College Algebra, Chapter 2, Section 1, Graphs of Basic Functions and Relations, Symmetry. Continuity. A function is continuous over an interval if it's of its domain if its hand-drawn graph over that interval can be sketched without lifting the pencil from the paper. This is a very simple definition and a good way to think about it. If a function is not continuous at a point, then it may have a point of discontinuity or it may have a vertical asymptote. Here are a couple of examples. The graph on the left has a point of discontinuity. There's a gap at x equals 2. The graph from the left has an open spot there, and then it kind of jumps up. And notice again, you could not draw that graph without lifting your pencil. The same for the graph on the right. This cannot be drawn without lifting your pencil, and again, the discontinuity happens at 2. This time we have what's called a vertical asymptote, and you'll notice that the parts of the graph on either side either rise really close to that or fall very closely to that line. Here's an example. We're going to figure out the intervals of continuity. In other words, using set notation, describe where these functions are continuous. Give this a try, pause the recording, and resume to check your answer. The first one is continuous over the entire set of real numbers, negative infinity to infinity. There are no gaps in that graph. Graph B has a point of discontinuity at x equals 3. In order to write the interval on which it's continuous, what we do is we go from negative infinity to 3, and then from 3 to infinity. The U-like symbol in the middle means that we're putting the two together to get the entire answer. And then C, there's a vertical asymptote at negative 2, so there is discontinuity there. And notice the notation is very similar to that of B. Now we're going to talk for a minute about increasing and decreasing. When a graph is increasing, the range values, the y values, increase from left to right, and the graph rises from left to right. If it is a decreasing function, then the range values will go down. The y values will decrease from left to right, and the graph will fall as you look at it from left to right. To decide whether a function is increasing, decreasing, or constant on an interval, you should ask yourself, what does the graph do as x goes from left to right? A little more formal definition. Suppose that a function f is defined over the open interval I. F increases on I whenever x1 less than x2 means that f of x1 is less than f of x2. In other words, lower x values give you lower y values, higher x values give you higher y values. This one's the opposite. F decreases on I if whenever x1 is less than x2, then f of x1 is greater than f of x2. In other words, as your x values increase, your y values decrease, or as your x values decrease, your y values increase. They go in opposite directions. F is constant on I for every x1 and x2, where f of x1 equals f of x2. Constant just means that every x value gives you the same y value. In other words, an equation like f of x equals 2 would be constant, and the graph would be a horizontal line. And there are the examples: increasing, decreasing, and constant. All right, we're going to determine the intervals over which the function is increasing, decreasing, or constant. Be sure to write your answers in interval notation. Pause the recording to give this a try and resume the recording to check your answer. First of all, we're decreasing from negative infinity to 1. If you look at the graph from left to right, as you go along that line, you're going down. The graph increases from 1 to 3. Notice that while the 1 was not included in the first part, it is in this part, and that's because from negative infinity to 1, there's an open hole there at x equals 1. But then the second part of the graph closes the hole. It goes up, and then finally it's constant from 3 to infinity. Okay, we're going to be looking at a few functions. This is the identity function. The identity function is just f of x equals x, and it's a diagonal line. As with any line, the domain and range are both all real numbers. You see their graph, both hand-drawn and on the calculator, and then what it looks like, the values look like in a table. The function is increasing over the entire domain and is continuous. We also have the squaring function here, that is f of x equals x squared. The domain is all real numbers. The range, however, goes from 0 to infinity. The reason for that is, if you look at the graph, you see no y values being used less than 0. The graph decreases from negative infinity to 0 and increases from 0 to positive infinity, and it is continuous. Now a word about symmetry. If we were to fold the graph of f of x equals x squared along the y-axis, the two halves would coincide exactly. This property is called symmetry. Now the mathematical definition of symmetry is with respect to the y-axis, which this is because you're folding it along the y-axis, is that if a function f is defined so that f of negative x equals f of x for all x in the domain, then the graph is symmetric with respect to the y-axis. For example, you have f of x equals x squared. Well, f of negative 4 is 16, and f of positive 4 is 16. F of negative 3 is 9, f of positive 3 is 9. Anytime you put an x value into a function that is symmetric about the y-axis, you will get the same y value for that x as you will when you put in the negative of that x value. Now we have the cubing function. Here's what it looks like. It is f of x equals x cubed. You see the graphs and the table. Few facts about it. It increases and is continuous on the entire domain from negative infinity to infinity. The point at which the graph changes from opening downward to opening upward is called an inflection point. If you look at the graph and think of it in terms of maybe like a bowl, the left half before you get to 0 kind of looks like an upside down bowl. It's opening downward. The part from 0 on looks like an upward opening bowl, like it's sitting up like it should. It's opening upward. The point where that changes in the middle is called the inflection point. Symmetry with respect to the origin. This is a different kind of symmetry that we have with the cubing function. It says if we were to fold the graph of f of x equals x cubed along the x and y axes, forming a corner at the origin, so you're basically folding it in fourths, the two parts would coincide. We say the graph is symmetric with respect to the origin. One test I've always used is if you can take the graph and turn it upside down and it looks exactly the same, then it is symmetric with respect to the origin. The mathematical definition is that f of negative x equals negative f of x for all x in the domain. We'll show you what that means with some numbers. For example, if you're talking about f of x equals x cubed, f of negative 2 is negative 8. Well, negative f of 2, negative 2 to the third is also negative 8. And the same is true for 1. Negative 1 to the third is negative 1. 1 to the third, and then with a negative on front, is also negative 1. This is a little trickier than the earlier one, but similar idea. Now we can determine symmetry analytically or graphically. So we're going to look at how to do it analytically. We have x cubed minus 4x. We want to show that it has a graph that is symmetric with respect to the origin. So analytically what we do is we put in a negative x. So we have f of negative x is negative x to the third minus 4 times negative x. We work that out, and you can see how it's done there. And we end up with negative x to the third plus 4x. Well, if you compare that with the signs on the original, those are complete opposite signs. In other words, we could factor out a -1 and have negative x to the third minus 4x. And that x to the third minus 4x is what we started with. That's actually f of x. So putting in a negative x changes the signs on the equation and doesn't change anything else. When you graph it, you can see that it is indeed symmetric with respect to the origin. Next, we're going to talk about the square root function. Okay, here's what it looks like graphically and in a table. Okay, analyzing it, this graph increases and is continuous on the entire domain, but notice that the domain is from 0 up. If we have a negative under that square root, we do not have a real number. So the domain must start at 0 and increase. Now the cube root function. Okay, there's what the cube root function looks like, and you see the table. The cube root function increases and is continuous on the entire domain. Now it doesn't look like it increases very much, but that's okay. The point is that the further out you go, the larger it gets, the higher the numbers go. Now we have the absolute value function. Just to remind you, an absolute value turns everything positive. So the absolute value of x is x if x is already positive, and it's the opposite of x if x was negative. This is what the absolute value function looks like. And you'll note that it decreases from -infinity to 0. It increases from 0 to infinity. It is continuous on its entire domain, and it is also symmetric with respect to the y-axis. All right, symmetry with respect to the x-axis occurs if you can fold the graph along the x-axis and the two halves of that graph will coincide. Now, that graph is not going to be a function because the points are actually lining up vertically, as we've seen before, and it fails the vertical line test. This is an example of the graph of x equals y squared. And you can see that, again, it is not a function, but if you were to fold this graph on the x-axis, it would indeed match up. And you can see the values in the table there. By the way, if you're going to graph the entire graph of x equals y squared, you must solve for y, which means taking the square root, but you must use the positive and the negative of the square root to see the entire graph. If you replace y with -y in an equation and it results in the same equation, then the graph is going to be symmetric with respect to the x-axis. For example, x equals y squared. Well, if we put in a negative in front of that y, we have x equals -y to the second. Well, what they did was they actually kind of factored it out, but if you just think through it, when you square anything, it's going to come out positive. So x equals -y squared is going to be the same as x equals y squared, which is what we started with. Functions can also be described as even and odd, and this is actually related to the type of symmetry they have. A function f is called an even function if f of -x equals f of x for all x in the domain. In other words, if the graph is symmetric with respect to the y-axis, it's an even function. A function is called an odd function if f of -x equals -f of x for all x in the domain. In other words, if the graph is symmetric with respect to the origin. Okay, this is a chart summarizing what we've just talked about. Pause the recording and study the chart, and then resume the recording when you're ready to move on. Here's an example for even and odd functions. It says, decide if the functions are even, odd, or neither. You've got two functions there. Pause the recording, give it a try. Resume the recording to check your answer. Again, we did this analytically, so we put a -x in place of the x in A and tried to see what happened. And when we put it in, we ended up with the same function, but with opposite signs, which means the function is odd. For part B, you put in a negative x, and you end up with, well, not quite the same function you started with, and you didn't change both signs. So this one is neither even nor odd. Okay, we'll finish with some classwork problems. Pause the recording to try them and resume the recording to check your answers. Do this through the rest of the video.